Morning, everyone. Welcome to this webinar on steam boiler control presented by Spirax Circle. Today's session will be led by Nick Wisby. And as you all know, Nick is a very committed and result-driven technical sales support engineer with an extensive background in the engineering industry, boasting for well over 2 decades of experience in the technical applications, electrical engineering, control and instrumentation, and of course steam. So he's been part of Spirax Circle for about 7 years, and currently is based in Spirax Circle East Africa office here in Kenya. Nick's career started included positions in well-known companies like Bucket, Fluid Controls, Adley Systems, where he's worked across various sectors such as the pharmaceutical, oil and gas, and food and beverage, including healthcare. So today we will cover steam boiler controls, and in this session we will explore basically effective boiler control strategies, how they can improve efficiency, reduce energy consumption, and ensure safety in our steam systems. So a bit of housekeeping we will go through. This session is about 60 minutes. And we'll have a Q&A at the end of the meeting. Your microphone will also be muted throughout this session. And I would request, should you have any question, you can be able to submit the question through the Q&A panel, which is available to you. So the questions will only be seen by the hosts, and time to time we may be able to post them online so that you can be able to view them. And also it may not be possible to cover all the questions during the 15-minute Q&A, but we will reach out to everyone who has a question to ensure that the questions are answered. So with that, I would please advise you to complete the feedback form at the end of the presentation, so that we can be able to get back to you and also to share a link for this training session. So I will hand over to Nick so that he can start over, and I hope you enjoy. Over to you, Nick.
Thank you, Anthony. So thank you everyone for joining us today. Today will be our last one of the year. We appreciate that ourselves as well as our customers become very busy around this time of year. So it's to give you and us the space to concentrate on the upcoming ramp up for your processes. Today we will cover, as always, who we are, an introduction to boilers, energy saving and efficiency, steam fundamentals, basic steam design considerations, steam trapping, heat exchange, condensate management, energy and steam quality. I know that might look slightly different to your the contents that's been sent. I'm sorry, that's partly my fault. I've had some computer issues, but the subjects that are covered in the email are also in this. They're just named differently. So first, Spirax Circle, who we are. So we were first founded in 1888 by Herman and Sanders and Reinders, under the name Sanders and Reinders Co., which this later formed the Sarco of our name. So it's the first letters of the first surnames. In 1907, we opened our first office in the US, and it was called Sarco Fuel Saving and Energy Company. In 1932, we started manufacturing in the UK, and that's when the brand name Spirax was introduced, giving us the Spirax Sarco. We've been present in Africa since 1948, and our office in South Africa, I believe, has been open since 1964. Our East Africa office opened in 2016. So we have 145 operating companies, well over 10,400 employees, over 2,000 local service engineers, and we serve by distributors in over 66 countries. Our main manufacturing sites, we have 29 of them on 4 continents. and our global HQ is in Cheltenham, which is in the southwest of the UK. We also have 59 customer training centres. So there's quite a lot of companies that are underneath the Spirax-Sarco group. We are Spirax-Sarco, which is under the Steam Specialties. We own Gestra, Cotopaxi under the same banner. We deal with thermal electrical solutions from Chromolux and Thermalux, and we also own Watson Marlow. Again, we're a FTSE 100 company with a turnover about £1.4 billion per year. And there's over 30,000 products in our global footprint. Some of the services we offer and products are things that you will be very familiar with now. So BoilerHouse controls, clean steam products, humidification, steam traps, of course, and service. We do we offer on-site visits, inspections, servicing of equipment, and so on. And we know what we're talking about. This is actually one of our boilers. So this boiler is sat in the UK in our training centre. We interrogate it, we open it, we show you how a boiler works when you go for training in the UK. There's other sites that also have boilers. So we're practical as well as theoretical. So the basic steam boiler house design. So as you can see here, we have in front of us a kind of very simple version of what you will see in your boiler house. Center is your boiler with all your controls and your feed water in, for instance, your TDS control. We have flash recovery here, which we will also talk about, your feed tanks and various different equipment going off to your line, including your blowdown vessel. So typical steam and condensate loop. So as you can see, we produce steam in our boiler. We take it to a process. In this case, for this example, we're using a heat exchanger. When we've consumed the energy that's in that steam and it's turned back to water, to condensate, we then run that through a steam trap so that we don't get steam coming back through your system, and return it to the feed tank. Properties of steam. Why do we use steam and not another media? So it's a compressible gas, which means we can make our pipework smaller, therefore cheaper. It's direct pressure and temperature relationship. So you know at 10 bar you have 184 degrees, and that's always the case. High heat content, so its latent energy is quite high compared to a low temperature hot water system. It's 50 times higher and 20 times higher than the low temperature hot water system above 20 degrees. So water has a calorific value, an enthalpy value of 4.19 kilojoules per kilogram, versus steam, which is typically 2,200. So as you can see, there is a much higher energy, a much higher heat content in steam. And steam flows with pressure drop. So that means it doesn't need any pumps. By the condensing of steam in your process at the end of your process, that pulls a vacuum, which means that the steam will then fill that empty space, that void. So therefore, there's no need to pump the system like you would for water or thermal energy. Uniform temperature gradient along heat surfaces. So effectively, that says that if you have a 10-meter piece of pipe, it will be just as hot at the end as it is at the beginning. Heat transfer coefficients are 2 to 3 times higher than water. So it gives up its heat to a process 2 to 3 times better than water alone. And it transfers its heat energy by condensing. So as we said before, as it changes from steam to water or back to water, it gives up that energy so we can then pump it back. So review of principles of steam. So as you know, steam and pressure are related. So by generating steam at say 10 bar, we know that its specific volume, so the area or the volume it takes in a pipe is 0.2. So that's around 177 meters cubed. If we reduce that pressure to 2 bar, you can see that it dramatically changes. So now we have 0.6. It's much larger. So the sweet spot, as we would say, is between 7 and say 10 or 12 bar. After that, it costs more to put in the energy with very little change to volume. So most boilers will run between sort of 7 and 10 bar, because this is the area you see the most significant change. So as you can see, that's steam under pressure. So here we show the heat. So everything above the line in the red is saturated steam. Below that is water. As you can see, along the line, we both have condensate and water at the same time. So it's just showing the relationship there. As it condenses back into water, it gives up its heat. Do we have any questions at this point?
No questions at this point. We can go on.
Okay, so when we talk about the boiler house, we're talking at the beginning of the process. So before you've gone off to your heat exchange units, your AHUs, your end of line process, we're talking about this area here, and this is where we can make the most difference when it comes to energy saving. If we have an efficient boiler house, we have a cheaper to run boiler house. So main components of a boiler house itself is the boiler, the hot well, feed tank, and the blowdown vessel. Solutions typically supplied by us are shown in blue, and whilst we don't make boilers themselves, you can see that there is a considerable amount of equipment that goes onto your boiler that we supply. So atmospheric feed tanks. This is one source where you can make saving when it comes to energy. So why do we heat the feed tank? We heat it because we don't want to thermal shock the boiler. So there is a time when your boiler water runs low and you need to add more water to produce more steam, there is a moment, or there is a period of time where it's no longer producing steam, it's heating up to produce steam. So by heating the feed water, we limit the thermal shock, which means that the time taken to heat back up to produce steam is shorter. So as you can see here, we have one of our mixer units on the top. So here we've got heated. So we're maintaining the 85 degrees, round about the 85 degrees that we would like. The higher the temperature to a point, the less we need oxygen scavenging chemicals. So there is a saving that could be made there. And RO as well, but makes cleaner water, less chemicals needed to clean the water. This head here at the moment is bringing back your condensate, which is flashing off, but it's also mixing it in there with your cold water so that you have a warmer temperature coming into the tank. And because it's atmospheric, we have in it a head leading to normally outside the building. So feed tank design. So a well-designed feed tank. We'll have cold pre-treated makeup water that enters at a high level. So the reason why it enters at a high level and makes its way back to the bottom of the tank or near the bottom of the tank is so that as it bubbles up, as that steam collapses, it releases the heat and you can minimize the amount of steam or flash steam that you see coming off the top of the tank. It's controlled in a manner that the cold water is not driven to the bottom of the tank. So you have some kind of pumping device. You have a pump, a recirc pump, circulating the water there. Most boilers will will get their supply from the bottom of the tank. Heat rises, so the hotter water, if it's not recirculated, is here. The boiler is then drawing from the cooler water. So to prevent that, we would put a recirc pump in. So we allow the circulation of the system, as it shows here, to mix the water so there is a more even temperature across the total volume. This means that there is less likely to cold dose, to thermal shock your boiler. So they operate within a temperature range, so chemical dosing can be regulated. That means that we can minimize the chemicals. have steam injection, so this red pipe here, to maintain the temperature. So for any reason, if your condensate is cooler than is adequate to bring it up to around 85 degrees, we can inject steam into the tank and bring that temperature up. Has condensed at low level as the oxygen is free, so effectively it's just saying it's warmer so that there's less chemicals needed to scavenge the oxygen. And direct steam injection, excellent insulation, anti-stratification pumps. So all of this is to protect your equipment. So here we can see a boiler. I don't know why it's not playing. So typical boiler here. So on this particular case, we have an economizer. An economizer is designed to preheat the water before it goes into the boiler again. So this tank is, imagine it's set at 85 degrees. We bring it through the pump, which will be an anti-stratification pump, because where you have a pressure differential here, you can have cavitation on the pump. We then bring it round to the economizer, which uses the heat being released through the chimney to heat the water further and then send it to boiler. So on this, we have a 3-pass boiler. So when we say a 3-pass boiler, we have the burn tube. Then we have a series of pipes. Many of you would have opened your boiler and seen those. So the fume gas is passing through the boiler 3 times. So we call it a 3-pass boiler. So if the boiler level drops below the flame tubes, we have an issue there. That's why we need to control the level there. And the flame tubes begin to melt and crack. So if you drop your water below the required level for your boiler, you start introducing more risk. So what happens is the flame tube no longer is heating just water, it's heating the tube itself. That can then become to a point where it becomes more viscous, where it becomes no longer solid. That would collapse as water enters the flue or the fuel chamber. It expands because of the sudden differential in pressure, and that's when you have a critical boiler. So as it sees here, flash steam blows the burner out and thrusts the boiler forward. So it acts like a rocket, and you end up with a messy situation on site. Of course, this happens when sudden release of energy would be catastrophic. So fortunately for modern steam boilers, they have a number of different safety mechanisms to prevent this happening, which means they need to be maintained. We unlikely to see the catastrophic circumstance of a boiler blowing these days, but it means that we need to be more vigilant on the equipment we use on that boiler. So what's needed for level controls? Before I move on to that, is there any questions?
Yes, there's one question from Stefan, and the question is, for preheating the water in the feed tank, how is this usually accomplished? Electric, gas, heat exchanger, that is heat recovery, or what?
So it can be one of those, or it can be all of those. Most of the time, the steam systems themselves are used. So when you're talking about the injectors, let me just go back and we'll, so I can show the example. So when you're talking about the injectors, they tend to be steam. It tends to be a mechanical operating control valve there. So this is filled with a fluid which expands and contracts to close the valve. That would be a steam feed from your system. You could electrically do that. Gas, not so much. The reason you wouldn't use a fuel source like gas, HF, heavy oil or anything like that is you're already using that in your boiler. You would increase costs. So the steam system itself is already operational. It makes sense to use what you have. Also the heating, the flash off of your steam system, your condensate when it's returned. So by returning as much condensate from your trap system as possible, or your condensate system, you are bringing that energy back. So not only are you saving on water, but you're saving on heat. So it can be an indication, flash off on your tank of leaking traps. There's a difference between a slight wisp, as we say, so a very slight steam coming off the top to something that looks like it's under a bit of pressure. All of these mechanisms you already have in place, so most of it is just good maintenance and return of your condensate, plus the injection of steam if you need to top off that temperature higher. Hopefully that answers that question. Is there any others?
No, so we can proceed. Thank you.
So feed level, so level controls and alarms. The reason we need to accurately control the water level is to ensure that the steam is being produced efficiently. So we want to get as much, as we would say in the UK, bang for our buck. You want to spend the least amount of money and produce the most amount of steam. So modern steam boilers are far smaller than the boilers of, say, 50 years ago. I don't know if any of you know of or have seen the old Lancashire boilers. They were the size of a small locomotive. They were very reliable, but they were also very inefficient. We need to maintain the correct water level, as we know, because the boiler is essentially a cylinder laying on its side. And it tells us that if we don't have the exact water level, the surface area requirement for making steam is incorrect, but also we introduce more danger into the system. So as you can see here, as we've seen before, so we have your feed water coming in. There's, in this particular case, there is a control valve, so this is modulated, and we're maintaining a water level above the fire tubes, but as low as we can, so there is more surface area to be able to convert to steam. If we have this overfilled too high, there is less surface area, so therefore less steam being produced. If we have it too low, we expose the tubes, which then introduces a danger of overheating. So we need to hit that at just the right spot. So as it said here, as I said just a minute ago, if it's too high, the surface area is too small, too low, more danger. So level control. So for accurate and reliable level control, it's essential that we both safely and efficiently control the water in our boiler. So many of you will recognize the sight glass that we have there. There will be markings for a normal level. Then we have two other levels maybe marked on here, which one will shut down the pump and the other one will turn it on. So this is on-off feed water control. So there is an area of cold dosing going on between when the pump turns off and when it starts. And the happy medium where we would like the boiler to be is at the normal water level. So somewhere in the middle. So as the first level alarm is low level is hit, you have an alarm sounder and the burner should shut down. So making the boiler safe. It's no longer producing steam. There's no longer a flame on the tube. The boiler will then refire when the water level increases, but not before. Our second low, however, when the boiler reaches our second low, there will still be an alarm that sounds and the boiler shuts down, but the boiler will not restart until somebody manually resets it. And that's to encourage you to check your water level. There is an issue there that has now become critical. So again, we can have further alarms. In this particular case, we're showing a high level alarm. So when we talk about the surface area, we don't want carryover. We don't want water to spill over or into our steam system because it corrodes. It turns into erosion, corrosion, chemical in the line, all those kind of things. So some boilers will also have a high level alarm, which will sound and the burner will effectively shut down again. The level controlled between these 2 points. So as you can see, we have a pump off and a pump on. As we said before, this is the sweet spot where we want our boiler to be controlled. We don't want to hit our first or second level alarm. We also don't want our high alarm. So we want to control in between this area. Is there any questions at this point?
Yeah, we have two questions. The first question is, where is the chemical dosing, or rather chemical dosing should be done at the feed water tank or the cold water line?
So it's normally done, there's normally a pre-tank before the feed water that then feeds into the feed tank. It's normally done there. If you don't have that pre-tank, it would be done in the feed tank itself. You wouldn't see it on the cold water line, not really. There's no, you can have a measurement there. I would suggest it's probably more accurate at your feed tank or on the pre-tank. Certainly wouldn't be directly to boiler. Anthony, I don't know if there's anything you want to add there as well.
No, yeah, mostly they do, it's normally done at the feed water tank. On the instances where you can find on the line now to the boiler, having injection points where they put, but it will be not at the cold water line, but at the feed tank or the line now to the boiler itself.
Yeah, so it's we want it to be hot because if you were dosing, for instance, on the cold water line, one of those chemicals would be oxygen scavenger. You'd use more chemicals because it's cooler. So at the feed tank, you would tend to do that dosing because then you would use less chemicals. It's also more accurate. Any other questions?
Yes, there is another question. If the hot well doesn't have a deaerator head, should the cold water still be introduced at the top, or?
So the pipe comes in on the top, but it's long enough to get significantly down on the low down into the feed tank. The reason being is if it's too high, if it's too near the top, what you'll find is without a recirc pump, the hot water will just sit at the top and it will never actually reach the feed into the boiler. So by introducing it lower into the tank, any flash off that comes out that pipe has a chance to bubble through the feed tank, releasing its energy and heating. And also you'll see less steam coming off the top. So you want to maintain as much as possible an even temperature in your feed tank. So we would suggest that although it's introduced from the top, the pipe is relatively low, maybe 3/4 of the way, maybe a bit more down the tank to allow the mixing to take place. Not sure there's anything you want to add there.
Yes, because when you have the condensate coming in back, and you know hot water rises, if you put it at the top, we've seen cases where you find a feed tank has very hot level at the top and very cold sessions. That's why we normally even put the resac pump. That's basically what Nick said. It's a recirculation pump. You're able to assist the water in the feed tank to be well mixed and have a uniform temperature as maximum as possible. For cold water, yes, if you put it at very bottom, it can stay at the low. So if you introduce at the highest side, then it will be able to mix. But it's normally better if you have a deaerator, because we can be able to mechanically deaerate that water as it goes into the feed tank, basically to remove the oxygen. Yeah, so it's normally advisable to have a deaerator. Yeah.
It's effectively a preheat to your cold water feed in the deaerator head. So it's by mixing it as it's entering the tank, it's transferring energy and allowing the cold water to be at a higher temperature.
Yeah. So there is another question for the water level control. Will conductivity probe still be effective when using raw water as feed water?
No, so your conductivity would be too low. You normally would use resistivity with RO water, so you need a minimum level of 5 microsiemens. You'd see that in the boiler because by the time you've introduced the chemicals and things like that, you've got your conductivity required. But before that, it's very difficult to register the correct reading. and be able to monitor the level properly. I'm not sure you want to add there, Anthony.
Yeah, we normally set at 5 microsiemens. Anything above that, our sensors, the probes, that is, if it's in the water level, can be able to detect basically the feed, to be able to detect the water. Yeah. So in most cases where you have anything above 5 microsiemens, then the conductivity probes will still be able to work.
Yeah, so I'd like to highlight that's not just Spirex, that's all probes of that type. So they all struggle there. It doesn't matter which manufacturer. It also, when you have RO water, mag flows, mag meters are difficult to use as well because they lack the conductivity for the meter to be able to see.
Yeah. The other question is, if the first low level and high level are too close, can it affect boiler steam output?
So in perfect conditions, in normal running conditions, hopefully you'd never hit your first low, but it can. If you suddenly have a process that demands a high level of steam, there is the potential that the boiler controls can't keep up with the process. So you see a significant dip down to your first low, which then fires your boiler. It can be an indication. I say can, it doesn't mean it is, but it can be an indication that your boiler is either too small or your process is drawing too much. The second low level should be at the critical point. So by having them too close, you will introduce the boiler effectively shutting down and having to be manually reset sooner. But the level controls are normally set by manufacturer, so they should be at a reasonable distance. Again, if you're hitting your second low, there's a challenge there that needs to be looked at. It could be that your process is drawing too much too quickly, or that your feed water supply is inadequate. So it would require more investigation. If it is a challenge for you directly, then please get in touch and we can come visit you and help. Anything you want to add there, Anthony?
No, that is quite well explained.
Okay.
Thank you.
Any other questions?
There are no more other questions, so we can proceed. Thank you guys for the questions and keep them coming in.
As we said in previous webinars, we love your questions. We love answering them. We want to interact with you. So please feel free to ask as many questions as you would like. So level control mounting. So here is the Mowbray switch. Many of you would have these on your sites. They're mounted on the side and the chamber is external, either external or internal. Level controls are mounted directly to the shell of the boiler itself or in external chambers, as I've just said. When mounted directly, they need to be fitted with protection tubes to dampen down any swirl or turbulence. So as your boiler is heating, anyone who's seen a kettle at home, as the water starts to boil, the water becomes very turbulent. So we need to factor in for that when we do our level controls. We don't want these going up and down and switching on and off our pumps or our low and second low levels. They need a true and accurate reading time. So remember that your first and second low level probes need to fit independently. So they need to work separately, which is why we often see 2 or more chambers insertion points. So because you need your second and first low to be independent, as the picture shows, you will end up with 2 points in your boiler, not 1. So on this, you have our LP10-4, which is a probe we have, which has, I think it has four different probes onto it. So on the first one, we've got our pump on and off and our first low alarm. And to keep it independent, we have our high level alarm on the second one on your right and our second low level alarm so that they work independently. just quickly, the reason why these are independent is if this one fails for any reason, we don't want the second lower level alarm to fail with it. So we need to have some kind of safety mechanism that makes sure that no matter what, there is always an alarm and a boiler turn off. So as you can see here, we have the steam system here with magnetic floats. So we need the first low and the second low alarm, and then also we need the level control probe mounted in at least two of the chambers or protection tubes. There are a number of different level control types, but the most popular used is the steam boiler mag float conductivity or capacitance probes. So conductivity, high standard or high integrity, and capacitance and magnetic floats are the others. So on-off feed control. So as we mentioned previously, there is quite a volumetric difference. There's quite a difference between your pump off and your pump on positions, meaning that the large mass of cold water is being added to your boiler. And then there is a demand. If there is demand, it can cause steaming rate to fall off dramatically. And during these times in peak demand, there is also a greater risk of carryover. So when you depressurize your boiler, you allow foaming on top of the water, which then has the opportunity to carry over in past your crown valve and into your system. And that foam will have various different bits of particulates that are in there. It will also have chemicals, so that will then lead to more erosion and corrosion of your steam pipes, which then could mean more maintenance costs. So we want to prevent that as much as possible. The advantage of on-off flow is cheaper compared to modulating. It's good for smaller standby boilers, so one pump per boiler required. Lots of starts and stops. And the pump will burn. The pumps can burn out with start-stop quicker because they are suddenly being turned off and then suddenly being turned on. And it has a high energy demand because of the inrush current you have on a pump between the primary and secondary starter circuits. You can use quite a lot of energy if your boiler is turning on and off frequently, or your feed water. So modulating is a little more expensive for the control. It's more accurate, therefore it's almost 6 of one, half a dozen the other, as we would say. So your pump is fired less. In real sense, you'll find that you effectively trickle charge your boiler. So there is a constant supply of water entering your boiler, but because it's modulating, it's keeping the level at a set point. It means that the energy on your pump arguably can be higher because it's constantly running, but the maintenance costs should be lower on that pump because there is less ramp up and ramp down. So start and turn off. So there's less damage and less inrush of current to your pump. So there is pros and cons to both. This is better for a boiler. Start-stop is sometimes better for energy control. And of course, we have the recirc pipe here. So for any reason, if we turn off this control valve here, we don't want to deadhead this line because you'll end up with effectively a shock wave coming back into the pump, which can damage it. So we have a small 1/4 inch line, 1/2 inch line, which then feeds back to your feed tank. So then when this control valve slams shut and this pump is starting to turn off, the pressure can make its way and vacate down to this pipe and back into your feed tank. Is there any questions at that stage?
Yes, there is. The first one is, what are some of the causes of failed Mowbray switches?
So there's a few reasons. They can just get old. Everything eventually fails, including me. There's the build-up of calcium deposits in the boiler if you've not chemically dosed it correctly, which can it makes effectively the tube that the float runs up and down in smaller, therefore it can stick into position. The float can perish, so it sinks. That would then give you a lower level than is actually in your boiler, which means that your feed water would constantly run. There's a few reasons. So all of them they boil down to maintenance effectively. So without adequate maintenance, so that's including the chemical dosing, all those kind of things, equipment will perish quicker. Yeah, we all have cars. If we don't look after our tires, they don't last as long. The boilers are the same, so the equipment around it is the same. Carry over, all those kind of things introduce challenges into the float system as well, because you have foam, so it becomes more corrosive. General maintenance, effectively. Anthony, I don't know if you want to add anything.
Yeah, routine inspection and maintenance is a key thing when it comes to Mowbray switches. If you start seeing that even they've started wearing off, don't wait until it fails, especially that float. It's just good to replace it. Don't operate it to failure, because to failure means it's going to be most probably catastrophic. So maintenance is key when it comes to Mowbray switches, where you have a lot of, especially if your water is bad. If you have bad treatment regime in your boiler house, then you will find a lot of sediments occurring, yeah, that can block this float. Yeah.
Yeah, it's the same as anything. With the reason why we strongly suggest you do preventative maintenance instead of at the point of failure is it's cheaper. So if something breaks, the damage it can cause to the surrounding equipment, be it the production line, the boiler itself, can be higher. So although it's painful to pay for maintenance, none of us like to pay money where we feel that we don't necessarily need to. By servicing it before it breaks, it costs us less than when waiting until it breaks. So we strongly suggest you have robust routines for maintaining and inspecting the equipment in your boiler. Any other questions?
Yes, there is another question. Kindly explain what to do in case of an imminent wood-fired boiler collapse, e.g., water line to the boiler getting blocked.
So run. Once you have reached the point where the tube is failing, there is very little you can do. The suggestion would be you need to make sure there is no longer firing and that the boiler is turned off. No more energy into the boiler means no more energy can be converted into a catastrophic incident. However, you do not know when that boiler is going to blow. You could walk into that boiler room and that boiler could go. If you are at the point where you are probably at no return, you don't want to be anywhere near that boiler house. When it has happened in the past, it's taken out not only the boiler house, but large portions of factory. These things go off. They're quite capable of killing people, especially if you suddenly fill a small space, such as a boiler house, with steam. The temperature is going to suddenly rise very quickly. And then your chances of survival will dramatically drop. This is why we want to catch it before you reach that point. You should hopefully, with proper controls, never be in a position where your boiler is starting to go critical. It should be isolated far before that. That's why your first and second alarm are so important. If you've gone past that point, I would suggest there is very little that you can do effectively. Therefore, you want to make the surrounding area as safe as possible, and that means not being there. Anthony, I don't know if you want to add there.
Yeah, basically there's very little we can do, but just to basically shut off the fuel supply, basically stop putting any more wood, and maybe close the air dampers if you have air dampers, and then just either cut off the power supply to the boiler if it's not possible, and then you just evacuate, because there's really very little now you can do at that point. But do not introduce cold water to the boiler, yeah, because it could introduce thermoshock to that boiler. So the best thing is cut off supply of the fuel and just evacuate the area for until now when the boiler completely shuts down. Then, of course, you'll now have to bring in a boiler inspector to come and see the extent of the damage.
Yeah, so we look after our boilers so we never reach that point. Even if you take out of consideration the human cost, so the lives that could be lost, a boiler going critical is expensive. The boiler's no good. The majority of the equipment that was connected to it is no longer any good. All that needs replacing. Plus the building structurally could be damaged. So it's far, far more expensive to us to not maintain those boilers and then go critical than it would be just to do the maintenance in the first place. So it's you should never reach the point where your boiler is facing being critical if your process is severely broken down at that point. So hence why we talk so much about level control and how critical it is. Any other questions?
No more questions. We can proceed.
Okay, so I'm gonna go at a slightly faster pace, only because I'm a little bit behind. So first level control, or element 1 level control. So as you can see here, there's 2 elements. So level control, metered system output. So suitable for sudden load changes under high demand. So this is you have your control here for your flow meter, or for your steam output. You have your normal level controls that you would have in place. By connecting them, if there is a sudden requirement for more steam, this will open more. There will be a quicker reaction time to in your boiler to creating steam. So this is what we call 2-element control. You have the first element here and your second here. So element 3, so this is a metered feed water. So it's the same as the 2-element you saw on the previous page. However, you are metering your feed water, so it's more suitable, more stable, and more efficient, so you get better quality steam. Must be a modulating supply on your boilers for this to work. So you have again, you still have your the same one on your steam and your level control in your boilers. We're also monitoring the feed water coming into the boiler here too. So that's the 3 points of control. So blow down. So in addition to the controls that you have for level, you need to remove the buildup of sludge that we find at the bottom of a boiler. So we will blow down our systems either once a day or once a shift if you have more than one shift a day. So if you were running 2 8-hour shifts in one day, you would blow down that boiler twice. So this is to remove effectively the chemicals that are in here. So the feed water will introduce impurities such as salts and chemicals, some solids. You have a buildup of TDS in your water. So you have your TDS blow down to maintain that. But as those chemicals capture the particulates we have in that water, they will sink to the bottom of the boiler, and that's what we need to remove. If we do not blow down this boiler, this eventually would build up, so it then becomes around your fire tube, which then, because there's no water cooling that surface, could end up with it heating and therefore collapsing. So as we show here, the buildup of sediment is now touching around the fire tube, and we want to get rid of that, to remove it as quickly as possible to ensure that it won't back up and affect the heat transfer of the fire tubes. So bottom blowdown, we can do manual. So in this case, we're showing manual. If you have 3 boilers in a boiler house, there should only be 1 key. And the reason being is you should only be able to blow down 1 boiler at a time. So with Spirax-Sarco valves and with many other blowdown valves, the key is removable, and it's actually, there's a springing there that stops you from keeping the key inside the valve. That makes sure that you can only blow down 1 boiler, and when it springs out, it's closed. So automatic boiler control. So we can have a timer unit, which say that you're blowing down once a day. You know you need to blow down for 10 seconds. You'd install the timer unit and a similar valve, as you can see here. This particular one is pneumatic. Timer unit would then fire the valve, open the valve, blow down for 10 seconds, then shut again. This is the most accurate. For no matter how much we try, is always a delay in human actions. So if we say 10 seconds, by the time you've actually physically closed that key and we've responded to the time finishing, it could be 11 seconds, which means you've blown down more water than was required. Depending on the size of the valve, depends on the flow rate through it. So there could be a significant amount of water that's passed before you closed it. Computers, sadly, they are quicker than us. So a timer unit means that it's more accurate. Therefore, you save energy, you save water, you save chemicals and all those things. Any questions at that point?
No questions? No questions at this point.
So bottom blowdown should go to a blowdown vessel. So the legislation in East Africa is slightly different to Europe, but there is still a temperature, a discharge temperature that we are required to meet before we enter the drain. So how a blowdown vessel works is, as you can see, you have your blowdown coming into here. The hot water comes here, it then flashes off and we take that out to vent. The overflow for the blowdown vessel is lower on the tank, which, as we spoke about before, hot water rises. So only cold water is sent out to the drain. There's a mechanical control valve here, which adds cold water in here to cool down if we need to. And that probe will be situated in the tank as well to maintain the temperature. So many of you will see these. If you don't see a blowdown vessel, you may have a pit, so a hole in the ground that is doing the same job before it goes to drain. In the UK, this is under a guideline called BG03. I know many of you businesses use European and UK law. So if you want more information, please seek the BG03 guidance. So bottom blowdown vessels should be sized to boilers. So if you have more than one boiler, you'll need to size the blowdown of that to both added. So both volumes of both boilers. Your blowdown rate, or your way you size a blowdown vessel, is the distance between your first and your high and your low. So that's the volume of water that you can vacate out of your boiler when you're blowing down properly. So if you have two boilers, double the volume, double the size of the tank. Any questions at this point?
No questions?
Okay, so TDS. So we in East Africa, and I imagine across Africa, don't see TDS blowdown very often, but we would say it would be where it is as critical as bottom blowdown. So we want to keep the TDS level in this boiler as low as possible, or not as low as possible, but at sort of 3,500. That's when we know that's the sweet spot to keeping our boilers as healthy as possible. We don't want added corrosion, we don't want added costs of maintenance. So by introducing TDS control, we can keep the TDS level as per manufacturer's requirements. So I know I just said 3,500, that's kind of the standard default position of Spirax based on the manufacturers we know, but it's only the boiler manufacturer that can tell you the correct TDS rating. Is there any questions at that point?
Yes, there is a question.
Yeah.
So we have hot water meter for boilers. Is there a need to install also steam meter?
So it's to do with efficiency, effectively. So one way we can tell the efficiency of our boilers is correctly. The minimum would be a meter on your steam. So you need to know how much steam you're producing for the volume of water you've put out. Ideally, the correct way would be a meter on your steam, a meter on your feed tank or on your water supply to the boiler, and also a meter on your discharge. So you need to know all three to know how much efficiency you have in your boiler. again, if I have a fuel gauge in my car, I know how much it costs me to fill the tank. It also tells me how many kilometers I've got to that tank, so I know when to fill up again. Boilers work the same way. Without a steam meter, how do you know that your boiler is running efficiently? So I can tell that there's a problem with my car if I suddenly see that there's less fuel and I'm doing less kilometers per tank than I would expect. So it gives me an indication there's a problem with my vehicle. If you have a steam meter and various other meters in your process, it can give you an indication there is a problem. So when we go back to preventative maintenance, you're catching the problem before it becomes a process critical. I know it's expensive for meters, that's why many of us will avoid purchasing them, but for the initial cost can save us a fortune over time in the future. Anything you want to add there, Anthony?
Yeah, it's mostly, especially if you want to know efficiency of your system or your boiler. Yeah, so it's a key because if you have also the hot water, you'll not know in terms of TDS and all that. It will not be able to measure. You'd assume that you're generating all that is being converted, but in real sense, it does not necessarily mean that the hot water you put in the boiler is equates to the steam generated. So it's quite advisable to put a steam flow meter if you are going to look for accurate steam production monitoring, yeah, or energy efficiency. To be able to know that, then you need to have that flow meter, because that is the one is going to tell you how much steam your boiler is actually generating.
Yeah, so I would argue the same with your TDS as well. So if you haven't got TDS control, chances are high is you're sending a sample to a lab. So if that lab takes 4 or 5 days to get back to you, it's no longer current with the position of your boiler. The level may have gone up, but it also may have gone down. So you'll base your chemical dosing on that analysis you've got from that lab. Because of the delay by sending it, it could cost you more money. So by putting a TDS blowdown system on there, you know the level, you know where it is. It costs you less to dose chemicals. Any other questions before I move on? Just because we're getting tight of time.
Okay,
Yeah,
sorry. So the other question is, blowdown for Viet steam generators have internal blowdown tanks. Would they typically also have cold water output, that is taking overflow from a low level?
I don't quite understand the question. Sorry. I don't know if you're more familiar.
Yeah, even this one's a bit. Maybe you can expand on that one, Stefan, to understand what you want to ask, so that you can be able to answer. So, but in the meantime, let me just jump to the next question.
Yeah.
On our boilers, separate economizer and preheater has been installed, used for in-feed water heating. We are using them at the same time. How this can be seen in terms, maybe I think it's in terms of steam consumption, because for preheater we are using steam. So maybe I can repeat that. On our boiler, separate economizer and preheater has been installed, used for in-feed water heating. We are using them at the same time. How can this be seen in terms of steam consumption? Because for preheater we are using steam.
So if I understand it correctly, the injector into the feed tank is your steam system, and then you've got an economizer on your exhaust from your boiler, then feeding into your boiler. So that's the correct way. The preheater, the steam injection into the tank will maintain the minimum temperature of around 85 degrees for an open to atmosphere tank. So you need that temperature to prevent the overdosing or the use of more chemicals than are required. The economizer is something separate. So after it's come from your feed tank and is on its way to the boiler, the economizer grabs more energy from the exhaust, the flume of the boiler, and then uses that to heat even more the water before it enters the boiler. So you end up with less temperature differential between what's already in the boiler and what you're introducing. So in terms of consumption, you can't think of the economizer joined with the feed tank, because the economizer is working afterwards. That's depends on the heat of your flume gas. But with the feed tank, the injector, the steam injection into the tank is what's required if you're returning minimal condensate, or if your temperature is too low. So remember, that injector is only being used if the feed tank temperature drops. If your condensate's being returned, say you've got 80%, 85% return on your condensate, you're going to be very close to that temperature anyway. So the injector isn't open. It only opens when that temperature drops. Anthony, do you want to add there at all?
Yeah, if it's as you've said, then the preheater basically it's for it can help in terms of also de-aeration, yeah, and the economizer is just to save on energy that would have otherwise be lost on the exhaust. So those can be two different systems that we are looking at.
So you want the economizer, the water temperature, to go into the economizer around 85, 90 degrees anyway, because that's the point where you see minimum decay of the materials that are there. So you would need the heating on the feed tank to be able to run the economizer properly anyway. Any other questions?
No other question at this point.
Okay. So TDS recovery, I'm going to speed through this. So effectively, we can flash off from our TDS and from our blowdown, we can capture that, flash off the energy and send it back into a deaerator head. We can also, from the blowdown that's coming through, run it through a small heat exchanger, so we can preheat the water further and bring that as a heating element into your feed tank. This is because we are wasting energy. When we send hot water to blow down and do nothing with it, it means that we've paid for that heat, we've paid for that energy, only to send it to the drain. So we want to recover as much of that as possible. As it says here, it recovers up to 80% of the heat energy from the TDS blowdown. Reduce fuel consumption, so you're preheating that water higher, so it costs less money to heat it. Reduces flash steam losses, because we're capturing those losses, and saves cooling water and effluent disposal costs, because the water is already cooler by the time it reaches drain. Steam boiler control testing. So as it says here, daily tests should be all level controls and alarms mounted in external chambers. Standard, not high integrity, so not protected. Controls and alarms mounted to the boiler shell. Weekly tests should be level controls, alarms regardless of mounted internally or externally. So once a week, no matter what kind of alarm you have, it should be tested. If it's external, it should be daily. The boiler daily control testing. So this is where we were going to talk about the sequencing of using a valve sequencer on a Mowbray. So as you can see, the controls are mounted in an external chamber. So we have the Mowbray float here. We can isolate the water between the boiler and the bottom chamber, and then use what we call a sequencing purge valve to prove that we can manipulate the rising and falling of that float. So we test that the float is working properly. This demonstrates it works and that there isn't any blockages. We're showing the image of a MagFlow on the screen at the moment, so it's fitted into an external chamber. Conductivity probe could be fitted, but this would be unusual, as it's taken the decision to, unless you've taken the decision to upgrade the controls. It's most likely that you've got the Mowbray floats working independently. I will stop for questions. I just need to speed through this bit because of time. So steam boiler daily control testing. So here again, for magnetic floats that are mounted internally, and then we can manipulate the float buoyancy by adding a small amount of water to test to a test cup mounted under the float for test purposes. And then the water drains away, the float regains its buoyancy, so it ends up back into the position it should. Mag floats, magnetic floats are declining in popularity. They're not used as much. I think they are more in East Africa or in Africa in general, just because the technology has moved on. The test facilities on other probes, other ones that we can use, are now becoming cheaper, more reliable, less maintenance. So steam boiler daily control testing. So here we've got the conductivity probes that are a standard type. In other words, without high integrity or self-checking features. Now we need to test these on a daily basis to ensure that they are operational. We need to lower the water level in the boiler. So you do that by blowing down by your blowdown. We then would see if the pump would turn on. And then when you can test the off, so the pump should turn off when it reaches its high level. We do not need to test a high level alarm, so you don't need to overflow the boiler on a daily basis. Steam boiler weekly control testing. So weekly test known as a true test or an evaporation test. This is undertaken by closing the feed water valve and then evaporating the water until the level drops to the first alarm. That then proves your first alarm. We need to check that the alarm sounds and the burner switches off, so it's no longer producing any steam. We then want to check the second low level. So we need to lower the water further to your second alarm, and then that should, by opening the blowdown valve again, and that then should isolate the boiler, so it needs to be manually reset. So these are different layouts for different boilers. As you can see, we have common boiler layout is here, so we go into a steam header. We have a 4-level header design, so it's going into the header and so fed into those, and then we have effectively dual redundancy, so you have 2 and 2 going into the same. So each takeoff point should have a non-return valve. This is to stop the backflow into a boiler you're not using. We don't want to pressurize the boiler that's not in use. One, there's a safety aspect there, but there's also a cost aspect there. It takes a lot of steam to fill that volume. We don't want to waste it. And steam metering, going back to the question you were talking about with steam. So it gives you a true picture of your steam consumption. Aids effective steam optimization. If you can tell when you're using your demands, then you can try to smooth out those ebbs and flows. Compact design and turn down ratio on most of these, on our meters, for instance, is about 100 to 1. So it allows full range and system conditions to be monitored. So I'm going to skip right because of the time, and we've overrun by quite a bit. I'm going to finish there, and I will leave you with some of the guidelines that we have. If you want copies of these slides, please tell us. We also have a lot of literature on PDF form that we can supply, so please get in contact. We have something which we call the Steam and Condensate Loop Book. We refer to it internally as the Bible. Has every piece of information you could require. And of course, you can contact us directly on the details that are now on your screen. I'm sorry I had to rush through that last bit. Time constraints are sometimes difficult, but I very much enjoy presenting to you guys, and thank you for the questions that are coming in. Anthony, is there anything we can answer now in our Q&A?
Okay, we do have one last question. Should 2 boilers with different capacity be connected to a common header?
So capacities, yes. Pressures, no. There's no reason why you could have a smaller capacity boiler which is acting as a boost to a demand that you have in your system. If you had a different pressure, then one would inevitably not be able to supply. There's no, again, in short, yeah, there's no reason why you can't use a smaller boiler as long as it's a backup. Anthony, I don't know if you want to add.
Yes, basically, I agree with what you've said. Different capacity boilers, you can put them in a correctly sized header, but should be same pressure.
Any other questions?
No other questions?
Okay. Again, it has been my pleasure to present to you. If you have any further questions that we failed to answer, or you've forgotten to answer at the correct time, and then it suddenly occurred to you to ask, please get in touch with us directly or fill in the feedback form, and we will reach out directly to you. So the more details you give us in the feedback form, the more likely we are to be able to get hold of you and help. So please reach out. Over to you, Anthony.
Okay, thank you very much, guys, and we really appreciate you attending. We will share the presentation. Just please fill in the form after the presentation, and we will be able to share with you the presentation. I thank you very much, and do have a lovely day and the rest of the week. Thank you.